All right, welcome back. So today we'll be talking about electric fields for point charge, and then we'll talk about equipotential lines, and capacitors, etc. Okay, so let's jump in. So for the a point charge, so we know a point charge will produce a electric field. So in this case, like this. Point charge produces electric field. So then under the electric field, if this both are positive, this B charge will be driving away by the electric force. So electric force does work. So there's a potential energy change. Okay, so there's potential energy change. You can calculate that. So normally you can do F times D, right? So which means QED. In here, the only problem is the force F, which is KQ on Q2 over R squared. You see from A to B, R is changing. So this is actually a varying force. So we wouldn't be able to do that. So that's why if you are not familiar with this sign, this is integration that's not supposed not to be in this class, but um, when you have varying force, then you will have to use calculus knowledge, which I will not go through in details because we are not a calculus-based class. But and the result, I will just show you the result for that. So change in the potential energy of the two, then turns out to be just KQ Q0 over RA minus KQ Q0 over RB. So that means UA then is equal to this term, UB then is equal to that term, okay? So if you get rid of the subscripts, then U will be equal to K Q Q0 over R, so that's the potential energy, then divided by Q0 because U equal to Q0 times V, so then V will be just equal to KQ over R, okay? So for the potential. Potential is a scalar, so which makes it nice algebra-wise, okay? Um, In this case, normally we say when the distance infinity far away, then potential energy is equal to zero because then it's not under the influence of the electric field anymore. So then that's equal to zero. Okay, so that's a convention, common convention for potential energy of zero for electric field. If it's involved also for gravitational field, we did the same in physics one, that if we are far away from our planet, then gravitational potential energy will be equal to zero. Okay. Now, because V is equal to KQ over R for point charges, so then at the location where the charge is sitting at, R is then equal to zero. So then electric potential at that point, then will actually diverge because KQ over zero will go to infinity. Okay, so if you have positive charge, then at the location of the charge, you actually have infinity potential. You can imagine as you are pushing two charges close to each other, right? And they cannot merge together because they will require more and more force, right? So then kind of potential energy actually blows up there. If you have negative charge, then potential energy by itself, that will be minus negative or minus infinity over there. Okay. Um, and so what we just saw was three-dimensional case. Now for two-dimensional, if we are just looking at potential in one dimension, then you'll see that at the charge location, this guy will blow up, will be positive infinity because it's K times positive charge over zero. And then at this location of minus Q, then it will be negative infinity. Okay, so it will diverge over there. And then in between, that will be just the sum of the two. You can do KQ over R1, which in this case will be X, and then plus K minus 2Q, Q being equal to minus 2Q on the second charge, divided by 1 minus X, or X minus, yeah, it's 1 minus X because that's the distance, which is a scalar. Okay, should be positive. All right, let's take a look on one example here, and then uh, you guys will be familiar with how to solve a problem like this. Okay, so I'm gonna to switch to my note here. So in this problem, it says, zooming in a little bit. it says you have this Q1 here, which is positive on the um, left corner, top corner here, and then there's this Q2, which is minus. Okay, so minus 2.1, and that means nano, 1.8, and C, that's nano as well. It's asking you what's the electric potential at point A and point B. Okay, so we have 2 point charges. So then electric potential by 1 on A, we can calculate that, and then we can also calculate for the electric potential on A by point 2. Okay, so in this case, we change color there. So V1A, it's a point charge, right? That should be K Q1 over R1. Okay, and then V2 is going to be K times Q2 over R2. Okay, K is a constant number. Q1 and Q2 are given. One is positive, the other one is negative. Okay, so R1 in here, this guy is R1. Okay, so this is R1. Now R2 will be this one. On the source there. I don't know why it's wiggling. Try again. Yeah, still wiggling, but it should be a straight line. Okay, so this guy is R2. Okay, R1 is the side of the square, so R1 should be just 0.1. Okay, so it's 0.1. R2 is the diagonal of the square. So diagonal of square, that would be square root 2 times the 0.1. Okay, so that times the I'm calling it A for the side 0.1, which this guy is A. Okay. So then we can then calculate for both of them, then we can add up for the total. Okay. So for part A, I think we can do it. So V at point A then should be equal to V1 plus V2, okay, which is KQ1 over R1 plus KQ2 over R2. So the K is the same, so we can put the K in before the parenthesis, and then Q1 over R1 equals to or plus Q2 over R2. Okay. They are scalars, so you can add them up directly. Electric field and electric force, they are vectors, so you cannot do that. You have to do their components. Okay, so we can just plug in numbers now. So 8.99 times 10 to the ninth, that's the K. Okay, and then Q1, that is positive 1.8 nano, 10 to the minus 9. Okay, coulomb over A, so which is R1, which is 0.1, and then now minus because Q2 is minus. Okay, so all you can do plus of whatever 2.1 nano times 10 to the minus 9 over square root 2 times 0.1. Okay, so that so you can punch your numbers in your calculator, but here actually 10 to the minus 9, 10 to the 9 will cancel these two 10 to the minus 9, so then a little bit less things to punch in. Okay, or fewer things to punch in. So this will give you about 28 volts. Okay, for this one. So this will be part A. Part B will be similar. You're just repeating, but this time now you're looking at electric potential at B. So this now becomes your R1. This is your R1, and your R2 now is this guy. Okay, so you basically just flip these two. Okay, and then so these two will be flipped, and then you'll find your potential at point B. Okay, so let's just do that quickly. So V at B now will be 8.99 times 10 to the ninth. Again, that will cancel out whatever is inside the parenthesis, 10 to the minus 9 there. Over now this time square root 2 times 0.1, and then minus 2.1, 10 to the minus 9, and then divided by 0.1. Okay, so there you'll get find your potential. Okay, so that gives you actually negative of 74 volts. Okay, slightly different. All right, so we'll go back to the slide. And then move on to next topic on equipotential line. So again, this is similar to what we learned in fixed one when we have gravitational potential involved. So then gravitational potential energy will be constant on equipotential lines. Okay, remember we have that contour map, which on the same curve of the lines, they are equipotential lines. So the gravitational potential energy is the same. The same here. So on the equipotential lines, electric equipotential lines, the electric potential is constant. So that means from here to here or to here on the same curve, they are all the same. But on different curves, they will be different. So like say this guy will be 5 volts, 10 volts, 15, 20 volts out, okay, like that. So the blue lines are the electric field lines. The green lines are the equipotential lines. Okay, so these two lines, when they intersect, they are perpendicular to each other. Because if you're going from here to this one, it's equipotential line, so potential energy should be the same. That means there's no electric work on the charge if you move a charge from here to there. Okay, so that means the line field lines and these curves should be perpendicular to that. Okay. All right. In the lab, this is what we're going to do in the lab. So there will be a positive charge and negative charge, and then you're going to draw electric field lines. We know that field lines start from positive charge and at negative charge, and then from infinity to negative charge, from positive charge to infinity. The green lines are again the just equipotential lines. Okay. If you have two opposite charges, so then in the middle, electric field is zero. These two are negatives, so field lines are coming from infinity to the negative charges. The green again is the equipotential lines. Okay, so on those lines, potentials are the same everywhere. For two plates with opposite charges nearby each other in the middle, electric field lines are parallel to each other, so um, they are constant fields there. So then the green line here be perpendicular to those. Okay, so remember electric field lines are always perpendicular to the equipotential lines when they intercept. Okay. So then if you have 0 volts on one side and then 25, 50, 75, 100, okay, on that. All right. So we have been mentioning the two plates next to each other. So actually a setup like that actually makes a capacitor, and it's called parallel plate capacitor. That's the simplest capacitor you could have. Okay. Now, if you have two plates, you can charge them with a battery or power supply. So then you'll have positive charge deposited on one plate and then negative onto the other plate. So then there'll be charges there. Field lines will be pointing from positive charge to the negative charge. So then you generate electric field in between these two plates. Normally, you don't see a capacitor like this, but you see like different shapes. Normally, you might have like a very two large sheet, and then in between something like this. There's an insulator, non-conducting material, separate the two, and then you can roll into a cylinder. Okay, so So then that would be normally what you see for a capacitor, okay? But um, the capacitor actually can store charge, and then it also stores energy. So that's why it gets its name. Now the charge in store on the capacitor is proportional to the voltage that it builds up. So if you have charges on the two plates, then you actually build up electric field, and then there's a distance there, so there's an electric potential difference V. Okay, so Q and V are proportional to each other with a constant number called capacitance of the capacitor. So C, it has a SI unit of coulomb over volts. It has its own name called Farad. So F. Okay. Thanks to Faraday contribution to the field. Normally you see something like this, a cylinder with two terminals, okay, connect to the two sheets, or something like this, like a button. It has like two metal plates separated by ceramic insulation there. A cable can also be a capacitor. So there's inner conductor, and then there's an outer shield conductor, and then there's dielectric there. So it will also um, uh, store energy there. These are some more capacitors you might be seeing. So like cylinder ones, or this one's also cylinder and disc, and then other different shapes. So they're basically having like two pieces of metal, and then separated by an insulator in between. Okay, let's take a look on this quick example. It says the charge on one plate of a capacitor is positive 30 microcoulombs, and the charge on the other plate is minus 30 microcoulomb. The potential difference is 400. So then what's the capacitance of the capacitor? Okay, so it kind of gives us already the charge Q 30 microcoulombs, okay, and then V is 400. So then um, capacitance capacitance C. Let's see. Let me change it to next question here. All right, this one here. So so basically C equals to Q over V. We are looking for that. So we can do 30 um, micro 10 to the minus 6, right? And then divided by 400 volts. And that will give us, we punch that into the calculator, 7.5 times 10 to the minus 8. Okay, and that will be in farad, okay, F. Okay, and normally you can say 0.75 times 10 to the negative 9, which is nanofarad. Okay, but that would be fine if you just write in like that. All right, let's go back to the slide. So the simplest type of capacitor, if you have two plates next to each other, and you can deposit charge onto the two plates, positive on one side, negative on the other side. Okay. The capacitance of this capacitor can be shown, which we'll probably do it later, not today, but its capacitance is, it turns out to be just proportional to the area of the plate, and disproportional or inverse proportional to the separation of D, with a constant number epsilon naught, which is called the permittivity of free space or vacuum, which is constant number 8.85 times 10 to the negative 12 farad per meter. Okay. So you can kind of think like when you have charges built up over here, it's not proportional to charge, because when you have charge built on there, now charge will produce electric field. So Q and V are proportional to each other. So when you do Q over V, actually they kind of cancel out. So it does not matter. Okay, Q and V does not matter, but leaving just the area of the plate and then separation of D. So if you are the two are separated further away, you get smaller capacitance, then they are close to each other. Okay, and the area also matters. So a lot of times you have two sheets that's very large in area, and then you roll into a cylinder, okay, to save space. But the two are actually very close to each other. The two plates are close to each other, okay. Um, so C equal to Q over V. Now let's take a look on when you actually have insulator in between. Okay, so a simple one is just two plates with vacuum in between. But what if you put insulator, which is called dielectric? Um, so in that case, what happens? Now insulators inside of insulator, there's molecules. So if you put the insulator in between the two plates, which is having electric field, molecules of the insulator will be polarized. Okay, so this is more positive, negative on this side to the positive plate, and then positive this side to the negative plate. Now, electric field originally parallel to each other. Electric field starts from positive charge, then end at negative charge, right? And then now goes from positive charge and a negative charge, and then positive charge to negative charge, positive charge to negative charge. So you can see there's like a breaking lines there. So that means they are kind of field lines are reduced. So in that case, um, because of the polarization of these molecules. Okay. So then instead of having like more field lines, now you have fewer field lines because kind of starting from here and then ends there. And then in the material, they are close related to each other. So then because of that polarization, so electric field get reduced. Okay, so if you have reduced electric field, then potential across actually will be reduced. Okay, so this V will go down, Q stays the same, then this will go up. Okay, so in that case, so C will go up in once you have insulator in between the two plates. So it actually helps you to get more capacitance. Okay, for the capacitor. So for insulators, if you put into the electric field, now the electric field being reduced, so then the amount, how much field is reduced, it will be original electric field divided by a factor that reduce the electric field, so then equal to the final. So this kappa here looks like K, but it's pronounced as kappa. Then it's called the dielectric constant of the material. It's also an intrinsic property of material. If you know kappa, you can find out what it is. Okay, just like heat capacity, density, those kind of properties for materials. Okay, so in that case, E then is reduced by kappa. So when you do Q over V, V will also be reduced by kappa because V is equal to E times D. D is not changing. Okay. So then this kappa will come up because it's numerator denominator in the denominator. So you flip up. So then it's kappa of Q over initial voltage, which gives you the initial capacitance. So final capacitance then will be equal to kappa times initial capacitance. That means it's then being enhanced by that multiple that factor. Okay. Kappa for different material, you can look at them up. For vacuum, it's just 1. For air, it's close to 1. And for other materials, you can look at them up. Okay. Now, insulators are not always non-conducting. If you put a lot of voltage, electric field, at the two sides of material, it will break down at a certain point. Okay, so to break air down, you need 3 million volts per meter of electric field to be applied. Okay, and then for other materials, you can see they are all in order of million volts, so very high voltage. Okay, there. Okay, so without dielectric, if the capacitance for the two parallel plates is as epsilon naught A over D, then with dielectric, it will be then multiplied by kappa. So then it will be kappa times epsilon naught times A over D, which kappa times epsilon naught is called epsilon. It's the permittivity of a specific material, okay? Relative permittivity of it. Let's take a look on this example. It says a parallel plate capacitor is made from two aluminum foil sheets, each 3.8 centimeter by 6.1 meters. Okay, so one is centimeter, the other one is meter. So you just need to convert one of them not both. Between the sheets is a Teflon stripe of same width and length that is 0.025 millimeter. Okay, again, this is not SI units, so you'll convert it into SI units. What's the capacitance of the capacitors? Okay, so without the dielectrics, we know that C is equal to epsilon naught times A over D. Okay, so and with dielectric, then we have to just multiply by kappa. Okay, and then kappa is given, so we can actually figure out. I think we have kappa. Kappa is 2.1. Epsilon naught is the constant number 8.85. So epsilon naught is 8.85, 10 to the negative 12 farad per meter. Okay, so this is the first time you see this, but that's given. Now A you can calculate, right? So that times that, and then D is given. This is D, so this is D. This will give you A. So we pretty much have everything. So we can just plug in the numbers here. So 2.1. By the way, kappa is dimensionless because it's the ratio of permittivity of material over actual permittivity of vacuum. So it does not have a unit. Okay. 8.85, 10 to the minus 12, and times area. So now 3.8 times 10 to the minus 2. Times 10 to the minus 2, because you need to convert centimeter into meters, okay? And then times 6.1 meters. Okay? Divided by D, 0.025 millimeter. So that also need to be converted into meters. Okay? So then you get 1.7 times 10 to the minus 7, and that's in farad. Okay, so that's on that. All right, let's go back to the slide and then move on to the next one. So again, the insulators, they don't always are not conducting. So if you apply a lot of voltage cross, then you'll break it down, making it become conducting. Okay, so for different materials, you can again look at them up here for AS 3 million again, and then for this different materials. Okay. All right, next we'll look at the energy stored in the capacitor, because capacitor stores both charge and energy, okay? So to look at that, we can think about two plates, okay? Right? When you charge it, you build in charge. So from 0 to the final charge Q, right? So when you are just starting to build out the first charge, if the first charge goes from one plate to another plate, so actually charging, that's the charging process. So you can think of charges are going from one plate to another plate. Okay, so basically that's what the when you charge a capacitor, that's what it does. Okay, so if you just charge your Q, okay, so then it will gradually build up, right? So because voltage is proportional to the Q you have, right? Voltage is proportional to Q you have. So as you have more and more charges over there, voltage goes up, okay, and then that. Now, for one Q and one V, right, from here to there, so then you'll need to overcome the work of Q times V, right? Because Q times V is electric potential energy, and that's actually the work done by the electric field or against the electric field, okay? So then 1/2 U then will be equal to just the total final charge times the average voltage, which then you can think will be half of the final voltage. You can then that will be just 1/2 of Q times V, final charge and then final V. Okay. Now, because C equal to Q over V, so then Q will be equal to C times V, right? If C equal to Q over V, then Q equal to C times V. So then this is 1/2 C times V, which is 1/2 CV square. Okay, the same thing. If we look at V is then because C equal to Q over V, so then V is equal to Q over C. So then 1/2 Q square over C. Okay, so then you can actually use one of these expressions to calculate the energy stored in the capacitor. Okay, so it depends on which two quantities you know or you can find out. All right. Let's take a look on the example. So this one says a parallel plate capacitor with plate area 0.0440 meters square and plate separation 85.0 micro. Okay, so micro you need to convert into 10 to the minus 6 meters to be charged to 12.0 volts and store 7.50 joules of energy. It's asking you what should the dielectric constant be between the two plates. Okay, so just trying to find my notes here, but um, let's see. So it tells us that the area, okay? So area is given, and it tells us separation, so that's D. Okay, so this is D, and this is area. Um, this is energy stored in it, U, and this is V, volts. Okay, so it says then what would be the dielectric? Okay, so dielectrics related to C, right? C is equal to the dielectric or kappa, looking for kappa. Epsilon naught is the 8.85 area and D. So we know A, we know D, we know epsilon naught, and we're looking for kappa, so that means we need to find C, right? Now it tells us that U is equal to 7.5. Now U could be, there's three expressions, right? 1/2 of Q times V or 1/2 CV square. Now we need to find C, so I think we can use that because U is given 1/2 CV square. It gives us this guy, right? So then we can calculate C first, and then we can calculate kappa later on. We can set up that U then equals to, and then there's another expression which is 1/2 Q square over C, which we don't need it at this point. But U equals to 1/2 CV square. So that tells us C then equals to 2U over V square. Okay, so a little bit algebra there. Just move things around and then you can find out. Okay, and also C is equal to that. So you can calculate that first and then put it back there. That's no problem. Okay, but just my personal preference. So I will just say now kappa, which is C epsilon A over D, then it's equal to 2U over V square. Okay, and I need kappa. So kappa then equals, you rearrange the terms, D goes to the right hand side, becomes 2U times D, and then V squared down here times epsilon naught times A. Okay, and then at that point I can plug in my numbers. So that's just my personal preference of doing the math here, but kappa then equals 2 times U given as 7.5 10 to the minus 6 joule because it says micro joule. If I remember that correctly, let's take a look. Yes. And then D is given as 85 by micro. Okay, so 85 10 to the minus 6 meters. Okay, that's D, that's U over volts V, 12 volts, 12 squared times 8.85 10 to the minus 12. Again, area is given 0.0440. Okay, so that at the end gives us 22.74 as the dielectric content. It's a number without units, okay, because it's a ratio between two of those constants. All right, so that's the full solution. And we'll go back to the slide there. Okay, so we'll just stop there. So what we learned today is for electric field for a point charge, that's KQ over R. And we look at equipotential lines, we look at capacitors, which for parallel capacitor is just epsilon naught times A over D, that's the capacitance. With dielectric, it's multiplied by kappa, it's become larger in that case. Energy starting capacitors will be one of these three expressions, okay? All right, we'll stop there for today. I will see you guys in next time, okay?